So today I'm going to talk about just some really basic electrochemical thermodynamics, thinking about potentials and equilibrium, how they determine equilibrium, and how they affect the driving forces for electrochemical processes. Okay, so when you think about chemical thermodynamics, right? So this is freshman chemistry. You have for example, reversible chemical reaction. So if I was to ask you, say as an undergraduate, what criteria do we use to determine if the reaction goes forward or backwards, if the net rate is forward or backwards? Well, usually, free energy, and this is the standard state free energy of this reaction, delta G of the formation of the products minus the reactants. Okay, so you know that. So, why do we use free energy as opposed to something else, right? And, free energy can be used to calculate, as we'll see, the maximum reversible work that can be performed by a system at constant temperature and pressure. So those are sort of the conditions that we often work at as chemists, right? Another key thing about free energy, right, Gibbs energy, is that it's minimized when a system reaches chemical equilibrium at constant pressure and temperature. So those are really useful features of the free energy. And why we use them in thermodynamics all the time, and why they're particularly relevant in electrochemistry. Okay, so if you're not at standard state, you have this equation, and we won't derive this right now, but you've all seen this, that the free energy of a reaction is the standard state free energy of that reaction modified by this RTL and Q. So what's good? So we typically write the product of the activities of the products, right, raised to their stoichiometric coefficient in the reaction. So divided by that of the reactants, right? And that activity, we can break that out into a activity coefficient, right? This is going to be the activity coefficient of species I. So the subscripts in our notes here are going to be sort of the species, a product, a reactant, a specific product, a specific reactant. I is going to be some species concentration over some standard. So usually in electrochemistry, we're often talking about things in solution. So the standard state concentration is usually 1 molar, but it can be really anything depending on what you want to do with your calculations. So, I like to think about activity coefficients, and I hope this doesn't hurt anybody's feelings. But to me, they're sort of fudge factors that allow you to use sort of ideal thermodynamic equations with non-ideal solutions. Okay, so that's the way I think about activity factors. And for dilute solutions, the activity factors typically go to 1, meaning you can ignore them and use concentrations. And if you take standard state to be 1 molar, you can just put in the concentration in molar and forget about the units and forget about the activity coefficients. Okay, but it's important to understand, I think, have a framework for seeing where this all comes from. Okay, so you guys know this too, right? Everybody knows that G equals H minus T delta S. This is the definition, right, of the free energy. So what does this mean in an electrochemical context? Okay, so how do we think about this? So what did we say? G dynamically reversible work that can be done, right? Okay, so if G is that, this is the maximum reversible work. You can think about H, the enthalpy of reaction, as the total heat released or gained. So if you're doing like water electrolysis, for example, maybe you guys have heard about the thermoneutral voltage, right? So what's the thermodynamic voltage for splitting water? We all know. So delta G is 1.23 volts. And it turns out delta H, if you calculated a voltage based on delta H, you'd get the thermoneutral voltage is 1.48 volts, I think, at room temperature. And so there's a total heat released or gained by the reaction, but there's also this irreversible part, this entropy of the reaction. Okay, and so that's one way to think about this. So I want to do this. I love this thought experiment, and this is from Barton Faulkner. Okay, so you can read about this in Barton Faulkner, which is a wonderful textbook, though has some challenges and actually learning from it. It's taken me a while to get really comfortable with it. So imagine you're doing this reaction. Okay, so what's getting oxidized? Well, zinc, right? Zinc's getting oxidized. Silver is getting reduced. Do you think this is a spontaneous reaction or not? Silver's a noble metal, right?
Yeah.
So if it's noble metal, it means it likes to be silver 0, or it likes to be in the 0 valence state. And zinc is actually a common chemical reducing agent, right? Zinc metal. So, as a chemist, we know this is downhill reaction. This is going to release heat, right, as it goes. So you can do this reaction in a calorimeter, right? So you could just mix zinc and silver chloride together and they would react eventually. And if you did it, under a thermodynamic way, so all species at standard state, you make the extent of reaction small, it's a thought experiment, and you measure the total heat released, you'd get delta H of reaction, okay? So, and that's negative 233 kilojoules per mole. So you can do the reaction a different way. Let's do an electrochemical reaction, okay? I don't know why my R's became big. Something happened there in the formatting. But you can do an electrochemical reaction. This is the calorimeter, okay? Here's the square that encompasses my reaction. And imagine now I have a zinc wire, I have a silver wire coated with silver chloride, and I have zinc chloride in solution. And so I can pass some current, right? And I can make more zinc 2 plus from that zinc, and I can take some of that silver chloride. Actually, I'm going to need silver plus in the solution too, right? Well, actually, the silver plus is here. I can take some of that silver plus and the silver chloride, and I can turn it into silver, right? So I can run the reaction, the exact same reaction. I'm just making the electrons go through the external cell. Okay, so this is a chemical reaction, and this is an electrochemical reaction because we make the electrons take a different path than the ions. That's the only difference, okay, in electrochemistry versus chemistry, right? Make the electrons take a different path than the ions. So here, of course, I'll still see the exact same heat. It's the same system, right? Nothing's changed, except some heat will somehow happen with the ions and some will happen with the electrons. Okay, so what's going to happen if I take two calorimeters? What am I going to measure? What if I put a calorimeter around this guy and I have another calorimeter around this guy and I measure QC and QR? What do you predict I would measure? And if this resistor goes to infinity in size, what you'll find is that the entropy term is what happens in the electrochemical cell. The free energy is the work you can extract. Okay, so that's actually a way you can really visualize what the free energy of an electrochemical reaction is, right? It's the external work you can do in an electrical circuit, if you want to think about it that way, driving this chemical reaction, but some of it's going to generate heat no matter what you do, right? It's going to generate heat in the electrochemical reaction no matter what you do, because that's the entropy part, okay? Okay, and of course, if I sum those together, I get the total. Any questions on that? Now, what if I change the load of the resistor? Then what happens? That's a good thought experiment. So what happens if I change the load of the resistor? Let's ask somebody else for potentials. So we might have an overpotential due to the cathode, an overpotential due to the anode, an overpotential due to ohmic processes. Let's make that subscript ohmic, okay? And these overpotentials, we could write these as I times RCT anode, or cathode in this case, right? So these are basically, you can model all these as equivalent resistances. So as you pass current, as the rate increases from infinitesimally small, you necessarily have to waste some of your free energy driving force inside the cell. So that's why when you discharge a battery at high rates, you get less voltage out, right? So that's so we won't get there, but that's how you understand this. And so in the thermodynamic limit, it's the delta G for the reaction is what you can pull out. Okay, so that's an important point. So hopefully that's a take-home point. Any questions on this from others? So that the Gibbs energy change is the maximum reversible work a system can do. It's really easy, right? If this is the maximum work you can do, well, this is the heat generated in the resistor. You can think about it that way anyways, right? It's going to be the charge passed times the voltage, okay? So NF is the number of charges per mole of reaction. E cell is the voltage. Charge times voltage is energy. Okay, right? Okay, so that's the energy. There it is. That's where delta G equals negative NFE comes from. It's just the fact that, when you pass current through an external circuit and it's all converted, in the case of a resistor, it would be all converted to heat. That would be the heat generated. Okay, so that's just NFE. And the sign is just because of our convention. So the sign's sort of, we just got to keep track of that. Okay, so let's see here. Now, we know that delta G equals delta G naught plus RTL and Q. And one thing to remember here is Q includes all species in the balanced reaction. So one thing, often spectator ions and things like that are dropped out, but you have to make sure that truly the spectator ion is in the same chemical state so you can drop it out of the balanced chemical reaction. So sometimes, for example, when you do an electron transfer, you form an ion pair. So the ion you you end up with is different than the ion you started with, so you actually need to put that in the Q. One thing to remember, that's a thing that gets confusing sometimes. And so we can use this now. We can, of course, get the Nernst equation. So you can just plug this in and rearrange, and here's your Nernst equation, right? So everybody's seen the Nernst equation. And that's where, of course, it comes from. You plug delta G equals negative NFE into this fundamental thermodynamic equation, and you have the Nernst equation, then you put it on a log base 10, and at room temperature, you get your 60 millivolts per order of magnitude change in Q. So in the ratio of oxidized to reduced species, for example, okay? Okay, so any questions on that? So I think everybody's seen the Nernst equation, but maybe didn't think that carefully about where it exactly came from. Some of the students, maybe. Okay, good, everybody got that? Okay, so let's keep going here. So let's consider an electrochemical reaction. O plus N electrons goes to R. Now, here's the Nernst equation, right? So I can write this, the activity of R, the activity of O. And I can, reformulate that as in terms of an activity coefficient and a concentration. I can pull those out, right? So here they are. I pulled them out of the log term. And when I do that, I can identify this term here as E naught prime. And so we call this the formal potential. And, often when you're making electrochemical measurements, this is what you're actually measuring is the formal potential. And that's because you don't necessarily know the activity coefficients. You assume that they're close to 1 in many situations, but they may not be. But we often are actually using formal potentials in this form, right? In this form of the Nernst equation. But it's important to make sure you remember that relationship between the formal potential and the standard potential, right? So the standard state, that's our reference states for all reactants and products. Okay, so I have a question for you though. Why are there no electrons in this Nernst equation? I said here, here is a delta G. Okay, now this is a delta G for a whole chemical reaction. Okay, including both what happens at a cathode and what happens at the anode. It's a full chemical reaction. And this Q corresponds to a full chemical reaction. And, then I said, consider this electrochemical reaction. And I just put the activities of R's and O's here. Now, this is a chemical reaction. It's a reduction reaction. And I could write this as a electron in the metal. Okay. But actually, the way this is treated usually in electrochemistry using the method of half reactions is actually we don't actually treat this is a full chemical reaction. We're treating it as a half reaction. And so implicit in treating it in the half reaction is actually that these are no longer fundamentally connected to only this equation. They include also the reference electrode. So let's show that here. So what we really mean, what we actually mean is this. E versus ref, if I'm only going to put O and R, right, in my half reaction, O plus an electron goes to R. If I'm only going to put those for my half reaction there, then I actually mean this. I have to have a reference. So what does it mean to have a reference? Well, it means this. This is the actual equation to which the E's, Q's, delta G's correspond. If I'm going to use the hydrogen electrode as a reference. Now I can choose whatever reference reaction I want. And when I balance that reference reaction with the probe reaction, the working electrode reaction I'm interested in, this is an example of what I would get. I'd get O, N plus. I'm just giving it some positive charge, getting reduced by hydrogen, going to R, making protons, okay? And so the actual Nernst equation is this. So these are the E's. These are the E's that are actually connected to delta G. Okay, these are connected to delta G. So these E's are also, they're connected to the delta G too. It's just you have to write the full equation. You can't just take this equation. You have to consider the full chemical equation, including the reference electrode. Okay, so this is another thing that confuses people a lot. And it's actually really important to get this straight. So whenever you're using like a half electrode standard potential, what you're really doing, if I want to use delta G equals NFE, right? If I want to use something like this and look it up in a table, I have to know what the reference electrode is. in order to figure out what is the meaningful actual chemical equation that goes along with that expression, okay? So this is important. And now at standard state, the activity of protons and hydrogen is 1. So you know they drop out here, right? And you get kind of what you're used to seeing. Okay, so the key point is anytime you write a Nernst equation for a half reaction, you are in fact using a shorthand to represent the full reaction, including the reference electrode reaction. So let's talk about equilibrium in the chemical potential. Here's a reaction. And we said that the Gibbs energy is minimized when a system reaches chemical equilibrium at constant pressure and temperature. So how does the Gibbs energy for a substance change with the amount of substance you have? If it's a pure substance. So that's, just kind of a simple question, but, maybe the way I asked it was confusing. But if I plot the energy of formation or something, right? If I trap the Gibbs free energy, the Gibbs energy of a pure substance, it's basically going to be linear, right? With the amount of material. And we're going to call that the chemical potential of a pure substance. It's going to be the molar free energy. Okay, the molar free energy. We're going to call that the chemical potential. And we're going to use that because, I want to figure out when is the total Gibbs energy of this equation, when is the total Gibbs energy of this system going to be minimized, right? Because if I make a little more C and D from A and B, is the free energy going up or down? And it's only when, the change is essentially 0 in free energy are we at equilibrium, right? So the system's going to go to minimize this free energy. Now, what about a mixture? What would the chemical potential in a mixture be? Well, it turns out in a mixture, the free energy does not scale linearly with the amount in the mixture, right? So this is actually why we define the chemical potential in general as dGdN, the change in free energy with the change of the amount of the substance. Okay, so this is more formally here we want to do it at constant temperature, pressure, and keep all other components in the system constant in their amount. And we ask how much is the free energy change, just to add a little more of that. So as an example, right, I might add sodium chloride to water, right? And I could keep adding it and adding it and adding it, and the free energy would not change linearly with the amount added. Okay, it would follow some sort of thing like this. Let's go through this now. Okay, so this is the chemical potential, and this is basically like delta G RT ln K, right? Or delta G equal delta G naught plus RT ln Q. We'll get there in a moment. But here's the chemical potential. Here's the standard state reference potential, and here's the activity term. So this tells you how the chemical potential of a species changes with concentration or activity, and is referenced to some essentially arbitrary reference state. Okay. And so this tells you, okay, the chemical potential increases with concentration. So if you want a lower energy and you have a high concentration of something in spot A and a low concentration of spot B, what happens? How do you lower energy? And that's described by the chemical potential, right? Chemical potential increases, it's, balls roll downhill. Chemical potentials go for a given species will move to go from high concentration to low concentration, just like balls rolling downhill. Okay. And although we call this a potential, a lot of things in thermodynamics are called potentials, even though their units are energy and not a volt. And we'll get to that in a moment, the difference between these things. Okay. Now, so for chemical reactions, we can write the delta G of a reaction at a given temperature, pressure, and concentration of species as the sum of the stoichiometric coefficients times the chemical potential of each component. So again, it's products minus reactants, right? So products are going to have positive stoichiometric coefficients, reactants are going to have negative stoichiometric coefficients. So it's just products minus reactants times their stoichiometric coefficients to get the delta G of reaction. Okay, so this is kind of simple stuff, but this is under arbitrary conditions. This is not delta G naught, right? This is for any given species in any given situation. And so you can see, if I have a simple reaction like AA in equilibrium with BB, I can write delta G and I can plug in all that stuff, and you just get Q. Delta G naught equals RTL and Q. Okay, so that's where delta G naught plus RTL and Q comes from. It comes from this equation here. Electrochemical potential. And this is a commonly misunderstood concept because it's really actually kind of confusing. So if I think about chemical potential, this is a nice diagram my colleague Mark Lonergan put together for an electrochemistry class we teach together. And what determines mu? What determines sort of the free energy dGdN? Well, fundamentally it's the solving the quantum mechanics of the system, right? And the quantum mechanics, of course, the wave function is here. It has, a kinetic energy term, and it also has a V. What's that V from in the Schrodinger equation? Potential energy, right? It's electrostatic in nature, right? Yeah. That's an electrostatic term. So one of the things that's kind of confusing about electrochemical energy is we're actually going to partition the electrostatic effect. So imagine I have an ion and I want to know what is the free energy of an ion. Well, we're going to partition the effect of the sort of nuclear electrostatics associated that you would put sort of in the Schrodinger equation to calculate the energy of this ion with the sort of macro scale electric potential effects. Okay, so in physics, right, you learn about electric potential, electrostatic potential, and you might say, well, okay, I have a positive charge. What's the electrostatic potential field, or what's the electrostatic potential look like for a positive charge? You say, okay, well, I'm going to take a test charge infinitely far away, and I'm going to integrate over the field on the path as I move towards the test charge. And this will give me, as a function of R or something like this, this will give me electrostatic potential as a function of R. So this is sort of a classical electrostatic potential. And so what we're going to do is we're going to take the chemical potential and we're just going to add a term to it that's associated with the classical electrostatic energy of a given species. So this is critical for charged species. And of course, in electrochemistry, we have lots of charged species, right? So, if you're calculating the electrochemical potential of oxygen, it doesn't care what the macroscopic electrostatic potential is. So if you have some charge distributions that are, described by a continuum and far away from each other, it doesn't care. It's not charged. It doesn't affect its energy. But if you have a sodium ion, it really will. And that's how like a double layer forms, right? So we need the electrochemical potential to describe things like the double layer. Now, some people just include this term in the chemical potential, so the nomenclature gets very confusing, actually. But in general, in electrochemistry, we like to call this the electrochemical potential. This term, mu bar, you'll hear mu bar a lot, equals mu, the chemical potential, which we've described now, plus this electrostatic energy. And the reason we use this is because in electrochemistry, this is what determines driving forces, and this is what determines equilibrium, because these are the relevant things in electrochemical systems. Now, they're not the only things, right? I could write another thing here, right? Plus mg, h. Okay, there's another term for energy, right? But does gravity really affect electrochemical systems? No, it's not relevant. We don't need to put that term in there, right? I could write a term for a magnetic field effect on the free energy, right? I could add these other terms. And that's where it kind of gets confusing. There's nothing magic about the electrochemical potential. It's just those are the terms that are relevant in electrochemical systems. So that's why we use it. Okay, keep going here. So some properties of the electrochemical potential for an uncharged species, of course, the electrochemical potential is the same as the chemical potential. For any substance, this is the chemical potential. We've already defined that. For any pure phase at unit activity, we can write the standard state chemical potential. For electrons in a metal, we can write that the chemical potential is usually invariant with concentration. Okay, so this is a key term. So for electrons in a metal, because in a metal, there's so many states and there's so many electrons. All the changes in electron concentration happen at the very edge of the metal, so you never actually really change the concentration of electrons in a metal. So we actually, and at least in the electrochemistry I've done, we always ignore the activity term for the electrons in the metal. Okay, so that's what that's saying. And then this is a really important thing. Okay, this is I want, I tell my students, and I hopefully maybe you guys will pick up, appreciate this. But whenever you're looking at an electrochemical system, when you have a given species, say you have sodium ions and you have a piece of Nafion, and you have free sodium, and you have absorbed sodium, and you have sodium in your electrode. I mean, you have all these different sodiums. At equilibrium, their electrochemical potentials have to be the same in all different phases of your system. That is the definition of equilibrium. Okay, this is a really, really important concept for every given species. And if you take this as sort of your foundation, then you can actually start analyzing, fairly complicated systems at equilibrium first. And the way to analyze the electrochemical system is think about it at equilibrium, think about as you perturb it from equilibrium. Otherwise, you can get yourself really confused. So we'll do, this is actually from a paper that Shane and I wrote on, and we just published it. And it's really, it's all textbook stuff, but it's textbook stuff that's actually kind of hard to learn from the textbook. It just talks about these different potentials. And I'm going to go through some of this stuff. We talked about electrochemical potential, chemical potential, electric potential. We'll talk about some of the applications of those and kind of thinking about electrochemical systems. But if you want to read this, I think we sent out the link. It's an ACS Energy Letters paper. We not really a research paper. It's what perspective, I don't know what it's called. Some sort of commentary thing. Okay. So now I want to ask you maybe a little trickier question. Imagine I have an electrical circuit and you go in the lab and everybody's done this in their physics class and you measure something with a voltmeter. What are you measuring? Well, first of all, what's the units of what you're measuring? Voltage. Okay, so is this sort of what I'm measuring? I mean, is it the difference in this electrostatic potential as I move in a charge from point A to point B? Okay, so if you think about it, what's actually, if I'm passing some current through this circuit, right? If current is flowing through this circuit, what's causing the current to flow? Why do the electrons go from one side of the resistor to
difference in free energy? So
difference in free energy, not difference in electrostatic potential, because electrostatic potential is but one term in the free energy. Okay, this is really, 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 really important. Okay, and people get this so confused. Super smart people get this really confused. Okay, so this is really, really important. So if the resistor and the wire is the same material, so imagine I have a piece of copper. Okay, I have a piece of copper wire, and I'm passing some current through it, and I measure here and here. Right, I can measure the voltage there and there. Then I measure what I actually measure is delta mu bar of the electron. I'm measuring the driving force. I'm actually measuring how much current goes through the voltmeter. I'm actually measuring the driving force to push current through the voltmeter, and depends on the impedance of the voltmeter, the internal impedance. That's actually what, good voltmeters like gigaohm, teraohm, it draws very, very little current to make a voltage measurement. I'm measuring the difference between the electrochemical potential of electrons at point alpha and point beta. Now, I can work that out, and if they're the same material, these cancel, and then I get this. It's negative F delta phi, and then what I'm actually measuring, delta phi is in volts, and so what I'm actually measuring is delta mu bar E over F equals delta phi, and this is in volts. That's what the voltmeter outputs, okay? But that's only the case if you have the same material where the chemical potential doesn't matter. So like a counterexample, which I haven't put in here yet, imagine I have a piece of gold and a piece of titanium. Which one has more reactive electrons? Titanium, of course, right? Gold's a noble metal. So if I wanted to draw the work functions, okay. Oh, pH. That is why a pH meter costs so much compared to a Home Depot voltmeter. Yeah, sort of. Okay. So and you have a gold here. Okay. So if I touch these things, what's going to happen? Where are the electrons going to flow? Okay. So the electrons are going to flow from titanium to gold. Okay. And eventually they're going to, these levels, the Fermi levels, right? The Fermi levels equilibrate, right? Oh, Fermi levels equilibrate. They always equilibrate. Okay, great. So at equilibrium, the Fermi level is the same. So how did that happen? Well, you have to leave some positive charge in the titanium as the electrons flow to the silver and some negative charge in the gold, okay? So this leads to a step. So if I wanted to plot phi, right? And I think about my positive test charge, there's going to be a step in the electrostatic potential going across this interface.
Right.
Can I measure this with a voltmeter? What happens if I attach a voltmeter here and here? What do I measure? Do I measure phi contact potential? What do you think, guys? No, of course not. You can't measure that, right?
Because
go ahead, I mean,
because it would be in equilibrium.
Because they're in equilibrium. There's no driving force for electrons to go through the external voltmeter. There's a contact potential because, again, it's the free energy, not the electrostatic potential that drives anything to move. Now, in some situations, the electrostatic potential may be the only thing that matters. In that case, sure, you can kind of equate the two. And that's actually one of the fundamental problems in how freshman physics is taught that propagates through all the errors in electrochemistry. Because in freshman physics, I got confused by this too when I started learning this stuff because I didn't understand the difference. Okay. And so I started teaching this is when I finally understood the difference. So this is really, really, really important. Okay, so changes in total free energy, or at least the energy term that matters under the system we're looking at, drive transport. So this is the transport equation. And you can see it's actually really simple. It's the flux of any given species is given by the gradient in the electrochemical potential in this case, because those are the free energy terms that matter. And there's some constants out front, the concentration of the species, temperature, and the diffusion coefficient. Okay. And of course, this is the electrochemical potential. Here it is. Here's the chemical potential. So I can break this up. Oh, I forgot to edit the slide. Ignore the bottom part for a second. I can do this. I can evaluate this gradient. And if I do that, I get the drift diffusion equation. So you may have seen this in semiconductor physics, right? So the drift diffusion equation is just the gradient in the electrochemical potential. That's all it is. The Fermi level is actually just the electrochemical potential. That's what the Fermi level is. Okay. In a solid. The Fermi level is the electrochemical potential of the electrons in the solid. So the flux is given by a diffusion term. Now this is one dimensional, but I could write del C there if I wanted to, okay, in 3 dimensions. This is the, Fickian diffusion, right? Things move due to diffusion and things move due to drift. And now mu I here this is actually the mobility. It's related to diffusion coefficient by the Einstein relation. So these are related, okay? So it's just diffusion plus drift, but the other thing that's really important, this is something going back, maybe you guys have, I know Joel probably talked about this stuff, Werfel. So this guy, famous guy in the photovoltaic community talking about how to think about photovoltaics. I mean, one of the big points, what also is relevant in electrochemical systems is it's a little bit of an artificial sort of separation into a drift and diffusion current. I mean, you can certainly write the math that way, and you can write currents like that. That's fine. But the reality is there's gradients in free energy that drive transport. And sometimes when you artificially separate things, you can get yourself confused. So just make sure you come back and make sure it also makes sense and the free energy is doing what you think it should be doing. Okay, any questions about
Shannon,
that?
let me just jump in. You're absolutely right. And just let me amplify that if I may. A particle does not know if it's drifting or diffusing. It has no way of telling, actually. All it knows is it's looking for a place with a lower electrochemical potential, exactly as you said.
Let's consider something like the electropotential. So in electrochemistry, you measure a potential of an electrode. Well, how do you do that? So how do you do a typical electrochemical measurement? Okay. You have a reference electrode, you hook a voltmeter up, right?
Mm-hmm.
So, but now we know that a voltmeter measures differences in electrochemical potential of the electrons. So I can actually write now that what I measure is this. It's the difference in the electrochemical potential of the electrons between those two electrodes. Okay, that is fundamentally what you measure. And then what we're going to show here in the next part of this lecture next week, we'll show how we can now define the electrochemical potential of the electron based on equilibrium processes, or we can drive them out of equilibrium with chemistry happening in the solution. Okay, so a reference electrode, if you think about a silver wire, okay, a piece of silver, and you have it coated with silver chloride, what is happening there is I am actually setting the electrochemical potential of the electrons in the silver, because I can write this reaction, right? Silver plus, I guess I should start from silver chloride plus an electron goes to Ag plus Cl minus, right? So there's a reversible reaction, and I can write at equilibrium that mu bar of the electron in the silver has to equal the product. So the the products minus the reactants. So maybe I should just write, well, anyway, so if I take products minus reactants, and I solve for mu bar E, I get that it's, mu bar Ag in the Ag plus mu bar Cl minus in the electrolyte, in the what's called that solution, minus mu bar AgCl, AgCl. So this is actually what sets the electrochemical potential. Now you can actually figure out, like, how we'll do this example, how electrostatic potential shifts the electrochemical potential of the electron. So if that's how you can use a reference electron to sense electrostatic potential differences, because it's changing the electrochemical potential of the chloride is the way I like to think about it. So we'll talk a lot about this, okay? And then the fact that E and the reference electrode potentials, they're all, we can define them into any arbitrary reference. So say a standard reference potential table in term relative to, say, the hydrogen electrode. I can cancel out that reference mu bar in the difference between any two systems. So okay, I will